Hello and welcome to Toddcast number 10. This is the first one you're going to see me actually get really excited because this is where we start to actually get into the foundation of a lot of what we're going to do question wise and just thought wise. Not that everything else isn't has been useful, whether it's building skills, building knowledge base, getting exposed to molecules. But this is one of those skills that will carry over into biochem, OChem, and that is something called a Lewis, uh, or I'm sorry, Fischer projection. So we did Lewis structures. This is going to be our second way to represent things. So let me, on that note, click to what's known as a Fischer projection. You will see them most often with sugars. You can see them with other structures as well. But a Fischer projection, you have to be able to translate. And so if you look at something, whatever it is, stuffed animal, a box, a painting, whatever you're looking at, there's three ways you can look at something. You can look at head on, you can look from above, and then you can look from the side at kind of an angle. And so the way we draw molecules is going to be the same thing. We're going to have the dash wedge or the bond line with the dash and wedge method. That's going to be the side view, if you will. The Fischer projection is a top view. And then we're going to eventually get to something called the Newman projection, which is a front view. And they all tell us something a little bit different. But we have to have rules for how we look at things. So which side is left, which side is right, is something that we have to set as a guideline or a rule so that we can translate structures fairly quickly. Okay, so Fischer projections, just a way of taking a molecule and drawing it differently. So instead of a side view, we're going to draw a top view. And so that's, hopefully it'll be helpful to put an eye here to show it's looking at it. And this is an eyebrow, so I know this is the top. So you're looking down here, this is top of your head, this is where your mouth and rest of your body is looking down at this molecule. And so visualizing this, seeing it in your mind, the way things are going to fall into place is absolutely like imperative. You can do this. This is where models sometimes can be helpful at first. We're going to end up doing this in a lab down the road, and it'll make sense once you do a few of them. So it'll seem weird at first, but again, power through it, get good at it. So align your eye above the compound. There's no rule which way you need to align it. So you could put your eyebrow here and look at it the other way, but pick a way and stick with it. So we're going to, by doing this, say, usually we consider the top of your head the top. So I've just arbitrarily made this the top and your feet are at the bottom. So this is towards your feet. So this is the bottom of the Fischer projection. And then if you put your hands out with your eye lined this way, put your hands out, your left hand will come out of the page. So this is your left side. Your right hand would go into the page. That is your right side. So it's visualizing how this thing is going to turn into a molecule down the road, or turn into a different orientation, different perspective of the molecule down the road. Okay, so I know top. I'm just going to help myself by saying top, bottom. This is going to be left. This is going to be right. Okay, we'll see how this works out. So you're going to take this structure and you're going to squish it. You're going to stomp it. You're going to smash it down. And when you do, you're going to push these into a plane. So this angle is going to go away. No, it'll be 109. It's going to be smush. This H is going to go back that way. This OH is going to go this way. So again, from my perspective, this is still top, still bottom. This is still left. And this is still right. Okay. Now we're going to get rid of this carbon in three-dimensional representation because by smushing it, I've already decided what's right, left, bottom, top. So I'm going to draw it like this. The intersection point represents a carbon. We've gotten used to this, I guess, with other projections, but the things that dangle off the end, we leave them designated as what they are. Okay, now it's just a matter of rotating it so that it's in normal alignment. When we draw it, we want the top to be towards the top of the page. So this CH3 is on top, like we have here, top. This is left, this is right, and this is bottom. So it's a matter of keeping track of things. That's basically what the Fischer projection is. Smush it, get rid of the middle carbon, rotate it in a way so that the top is pointing up. You can do that, you'll be in great shape. Takes a little bit of practice. It might seem simple at first with a single carbon in the center. Gets more complex with sugars because there's multiple carbons. Okay, so again, here's my eye. Eyebrow on top, which means top is going to be up here, bottom's going to be down there. More complex molecule this time. Instead of having one carbon that's going to go away, we're going to have three carbons that are going to be intersection points. We've also introduced a dilemma here. Do I have it point up or point down? The other one only had one point, didn't matter. Up or down, I'm still going to smush it. But the rule, Fischer projection rules, you need to rotate everything so that it's all point up when you're looking from on top. So CH3 going up to this one, this is fine. So this one, notice it stayed the same. CH3 here, OH and Br, OH and Br. This one also point up, H and OH stayed the same, CH2H. But this one had to rotate. So we had to take this group, rotate it up, this group rotated up, and this point rotated up. So to rotate a point in the plane, pointing down to make it point up, it's a 180 rotation. So this OH, which was in back and pointing down, if it goes 180, can't make it all the way to the plane, so it's going to be in front and up. CH3, which is down and in front, it's going to rotate 180, going to go past the plane and back. So this visualization is a tough one. You have to rotate the molecule into the correct orientation. So making everything point up and then smushing it is what Fischer did. Though this is one of the hardest steps you'll do. So I'm going to take this structure and I have to turn it into this. So just make sure I'm doing it right. When I smush it, I have the intersection here, here, and here. And again, I want to say this is top, this is bottom. So if I'm looking like this, and I put my left hand's going to be pointing out. So OH, OH, and H should be on the left side of the line. Br, CH3, and OH should be on the right side. It's worth it to actually specifically label them. It's going to say this green dot, this green dot, this green dot, this green dot. These 5 green dots are going to represent that carbon, that carbon, that carbon, that carbon, and that carbon. This first one is right here. So we'll send it over. The second one is here, third one is here, fourth one is here, fifth one is here. So those represent that. That doesn't really seem like much of a surprise. Let's make sure we have the OHs and the H's on the correct side. So the ones with these blue circles, again, if I'm looking down on it and I put my left hand out, these would be on the left, the ones that are wedged and are bold wedged and coming out of the plane, out of the page. So these on the left side. So OH, OH, and H need to be together. So I'm going to bring those circles over. So there they go, 1, 2, 3. And then the Br, CH3, and OH, with their circles. This has to be on the right, right, and right. So right near the top, right in the middle, and right near the bottom. So there those are. So being very methodical is important first. And then also getting good habits. So rotate it in the right orientation, smush it down, and then rotate it around. So this has to go up to top. It says come down to bottom. So top, top. And then we actually don't put the bow ties on it, even though technically it is. So this is a good way to think about it, that Fischer, person made these, were bow ties. So it makes all the substituents bow ties. They're both coming out, but when we smush them, they go into the plane. Okay, so this representation, C3 here, OH, OH, H, BRC3 and OH, this structure here in the bond line, the dash wedge drawing, is the exact same in the Fischer. You're going to have to be able to represent molecules, recognize molecules, and show reactivity with molecules in multiple different formats, multiple different ways of looking at it. So again, side view, top view. So this is just looking at molecule from a slightly different perspective. And depending on what you're studying, sometimes it is important to know individually where everything is. So this view is best. Other times, just to bookkeep where everything is, this one might be easier to draw and easier to see. Three-dimensionally accurate, not so accurate. Okay, as mentioned, they are very common in biology. We deal with them for sugars. So this compound, and I'll teach a cool little mnemonic when we go over it in lab for memorizing it, but this is glucose, and I'm going to specifically say this is D-glucose. It may not mean much yet, but it's that D becomes fairly important. So it represents exactly what side the OHs are in this sequence. So this is a top view. So these are all bow ties coming out at me. And if I looked at it from the side, I would see structure it looks something like that. With that carbonyl and H here, I'd have H. Oh boy, that came out really bad. H and OH. And this one I would have OH because it's on the left, H in the back. So I'm going to just stop drawing because it's not helping anybody. But keep in mind the bow ties. So bow ties represent where everything is, and the dash wedge represents compound pointing towards the back. So this is glucose. Just quick mnemonic for remembering it. Ribose is all right. I really like ribose. It's all right. Glucose, as we'll learn. So if I put all my fingers to the right, I'd represent that. If I take my right hand, looking at my palm with my thumb up. So if I put my thumb here and call it carbon 1, that's my thumb. If you fold your fingers so that your fingernail, you can see it, this finger's out, this finger, you can see it, fingernail, fingernail. So if you look at it that way, you'll have your index finger pointing to the right, your middle finger pointing to the left, your index finger or your ring finger pointing to the right, and your pinky pointing to the right. That represents the orientation of those OHs. Good way to remember it. Ribose is all right. That hand position can help you learn glucose. And then fructose, another common sugar. Just we'll learn this for nomenclature, but this is an aldehyde, so it's called an aldose. Aldehyde sugar, ose meaning sugar, so sugars end in ose. So aldose, aldose. This is a ketone, so we call it a ketose. Notice that it is identical. Glucose and fructose are identical from carbons 3, 4, 5, and 6. 3, 4, 5, and 6. They just differ at 1 and 2. And so for anybody who studied glycolysis, there is a step where you convert glucose to fructose. You turn it from a ketone to, or from an aldehyde to a ketone, which means you're turning from one structural isomer to another. Hence, we use something called isomerase, a generic term for an enzyme that converts from one enzyme to another, or one isomer to another, excuse me. And so you might have even learned this in aldo-keto isomerase or glucose fructose isomerase. Depends on who's calling it what. But Fischer projections, we're going to see them when we deal with sugars. You'll deal with them a lot. So that covers this. Again, like everything, these come with practice. These are kind of fun in a, I don't know, in a learning sort of way. So that is it. Have an absolutely wonderful time studying this stuff. and I will see you at the next podcast.